Alright, hello everyone. So I wanted to do a couple extra problems on centripetal acceleration and centripetal forces because they're sometimes difficult and they're not... You need to do a lot of practice in order to get good at these. So I thought I'd do a few more here in this second supplementary video. Okay, this first one here is kind of a common... this is a common type of question that you'll see in circular motion, where you're asked to find some kind of a minimum or some kind of a limiting case quantity. So, question 40 from your text asks, at what minimum speed must a roller coaster be traveling when upside down at the top of a circle so that the passengers do not fall out? So that the passengers do not fall out. That sounds important. And you're supposed to assume a radius of curvature of 7.6 meters. Okay, so this is another example of something that is circular motion, but not uniform circular motion. And also, it's using this term radius of curvature of 7.6 meters. Of course, when you draw this thing out, it's a loop-de-loop, so it's not a perfect circle. However, what this radius of curvature just means is that, like, you could fit a circle inside of here, and its radius would be, say, 7.6 meters, right? That would be the appropriate thing. So, of course, even in the case of, say, like a racetrack or something, you might have an oblong, elongated oval that is semicircular here on the edges, right? It wouldn't have to be a full perfect circle. You would just have to know, right, this radius here in order to figure out quantities about, in order to use the centripetal force and centripetal motion procedures here on this end. Of course, that would not apply then on the straight parts. So that's what the radius of curvature is referring to. Now, it's asking for the minimum speed that a roller coaster must be traveling when upside down at the top of a circle. So I want you to pause the video, draw a free body diagram, and then think a little bit about how you might go about solving this. If you don't know right away how to do it though, then don't spend a ton of time on it. You can come back in a minute and I will solve it. Okay, I'll assume that you have done that you have checked it out on your own, and so now I'll go through it. So, okay, we're looking for the minimum speed that the roller coaster must be traveling when it's upside down at the top of the circle. Alright, now I've drawn here then my free body diagram. Up at the top of the circle there are two forces on the car, on the roller coaster car. There's a normal force between the car and the track, which is pushing down in this case, right? A normal force is force between any two surfaces, right? There's going to be a force between the tires and the track up here at the top. And then there's also the weight, which is also pulling down right here up at the top of the circle. So I'm going to choose my coordinate system such that the radial component is positive when it's pointing down, then. And I know from all that we've talked about centripetal motion, right, that the net force in the radial direction is just going to be equal to mass times the acceleration in the radial direction. And since this is a circular track, that could be set equal to the speed squared over RC, the radius of curvature. Okay, now the net force in the radial direction is going to be made up of two components. Right, it's going to be made up of a normal force and the force of gravity. Both of them are pointing in the positive radial direction. And so I can set the sum of these two forces then equal to mass times the centripetal acceleration here, as I've done there in this equation. And we're supposed to, the condition that we're given, right, is that the passengers do not fall out. Okay, what does that fundamentally mean? So, for the passengers not to fall out, it means that they're pressed against their seats, right? In order for them to be pressed against their seats, that means that the roller coaster car must be pressed against the track. Now, the quantity that, the physical quantity, the mathematical quantity that corresponds to that physical situation of the roller coaster car pressing against the track is the normal force has to be positive, right? The normal force is the force between any two surfaces. If the two surfaces weren't touching one another, then the normal force would be 0. If the two surfaces are pressing against each other, then you're going to have a positive, a non-zero normal force. So I could take this equation 1 here, and I could solve it for the normal force, and then just require that it be positive, and that would be a perfectly good way to find a minimum velocity. But I found that students are more prone to make mistakes when they're working with inequalities than equalities. So instead, I'll do it the way that I've done it over here. So at V equals, I'll just say, at V equals V min, the minimum speed, I know that the normal force is equal to 0. And so I can plug this condition then into equation 1. So plugging that in, I get then, for the normal force, 0 plus mg equals, and on the right-hand side I have a mass times, now I've plugged in V min squared over the radius of curvature. Now if I solve this for V min, I'll just multiply by RC on both sides and take the square root. I get V min equals root G RC, and plugging in 9.8 for G and 7.6, which is given to me up here for RC, I get that 8.6 meters per second is the minimum speed required to keep the normal force positive. So this is the hard part about these problems tends to be not doing the math. Obviously, there's only a few lines of math here, but just figuring out what these sentences mean mathematically speaking, right? So the passengers do not fall out. That means that must mean that the force that exists between those two surfaces has to be non-zero. That would mean that the two surfaces are pressing against one another. Okay, so let's do another problem that's kind of like this. Problem 51 in your book. A coin is placed 12 centimeters from the axis of a rotating turntable of variable speed. When the speed of the turntable is slowly increased, the coin remains fixed on the turntable until a rate of 35.0 revolutions per minute, at which point the coin slides off. What is the coefficient of static friction between the coin and the turntable? Okay, I want you to think about this for a minute. So if you have a record player playing and you have a coin over here sitting on the edge, right, the idea here is that this thing is going to go around, right, it goes around in a circle, and at some speed, eventually, this coin will get slid off, right? Of course, the thing that was keeping it in centripetal motion this entire time was this friction force that was pointing in towards the center, right? If this thing was rotating and it was completely frictionless, then the coin would have slid right off right away. So the friction force is what's keeping it in this circular path. Now I would like you to draw the free body diagram and try and solve this problem for yourself. This one I hope you can abstract from what you learned in the last problem and apply it to this problem here to solve this. But first, let's just quickly recap some of the things about frictional forces. So the force of friction, now here we're talking about static friction, is equal to mu static, the coefficient of static friction, times Fn, the normal force. Okay. Now, in this case, there's no inclined plane, there's no anything like that, so the normal force is just mass times gravity, g. So note here, right, the normal force would be pointing, in the picture that I've drawn here, it would be pointing up out of the page, right? So the force of static friction is going to be, it's mu s times the normal force, and that should actually be an inequality, of course, because the force of static friction can take on many values, right? When this thing is just barely starting to turn, the static friction force is there, but it's small, right? The thing is, at some point, it reaches a maximum value. And at its maximum value, the force of static friction maximum is equal then to mu s times the normal force, right? So here, when it's maximum, there's an equality, but in general, the static friction force is an inequality, right? It can take on many values. So that's interesting. This is an interesting point here. Also, right, note, there is no kinetic friction, but for the sake of completion, I will finish talking about that. So mu k times Fn, the normal force, would be the force of kinetic friction. And the force of kinetic friction is always expressed in terms of an equality, right, not an inequality. And mu k is always less than mu s, right? Note that this is mu, it's not u, as sometimes I see students writing it as u. It's mu, it's a Greek letter. And the coefficient of kinetic friction is always less than the coefficient of static friction. This just means that it's easier to, there's less frictional force between two surfaces that are sliding against one another than there is between two surfaces that are just set in place, that are static with respect to one another. Okay, with that in mind, why don't you go ahead and try and solve this problem? You can pause me. Okay, I'll assume that you have done that. Now, here I've drawn my free body diagram over here. Here's my free body diagram. And you can see there's just one force, right? There's this friction force pointing in, right? There's also a normal force that's pointing up and out of the page. However, that's not relevant for this free body diagram, given that we're interested in the acceleration outward toward the edge of the disk. So this would be a perfectly fine free body diagram. So I'm given here the radius of the disk. I am given what I just chose to call the friction, the frequency of the critical frequency, FCR, or F critical. So this is the frequency that once you get up to 35 revolutions per minute, then the coin starts to move. Now, a thing to remember here is that you're given this in units, that you're given a frequency, not a velocity, a frequency, and it's in terms of revolutions per minute. So you need to convert that into hertz in order to be working in SI units, and I do recommend always working in SI units. So I can multiply this by 1 in order to convert it, right? 1 minute is 60 seconds, so this thing in parentheses here is just effectively 1. Right, this is equal to 1. So multiplying 35 revolutions per minute by 1 minute over 60 seconds, you see that the minute there cancels out in the units, and I have 0.583 repeating revolutions per second. And there's another word for revolutions per second, it's hertz. So this is the critical frequency. And we are asked to find mu s. We're asked to find mu s. So let's find that. Now, the radial force here is going to be, the radial force here is just equal to the friction force, because that's the only force that's pointing in towards the center. So I can take the frictional force is equal to mu s, the coefficient of static friction, times the normal force, and the normal force in this case is just mass times gravity, the weight of the coin. So if I take mu s mg is equal to mv squared over r, then I can take and cancel out on the left and right hand side of this equation the mass m. So if I take that and cancel those two things out, I would end up with a mu sg on the left-hand side equals v critical squared over r. So just taking and canceling out the two masses there. Now, if I then divide both sides of this equation by g, I would have that in the denominator. On the left-hand side, I would just have mu s, the thing that I'm looking for. So right now, I know g, I know that r is 0.12 meters because that was given to me. Now I just need to get from f critical, which was given, to v critical. So remember that v, in the case of uniform circular motion, and so here you can treat this as a quasi-static. There is an increase, of course, in the rotation rate as this thing goes around. However, you're told, right, the turntable is slowly increased. So you can treat it as if it's uniform circular motion at any given kind of point. Think about the rate at which the circular motion, the centripetal acceleration is increased, is a lot slower than the rate at which this thing goes around. You want to think about, this thing goes around, say, 10 times before there's maybe an appreciable increase in this friction force needed to keep the thing stuck in place. So anyway, I can use the equations then of uniform circular motion, and uniform circular motion tells me that velocity is 2 pi r over t, the period, and that is just another way of saying that it's 2 pi r times f, the frequency. So the critical velocity then is just the critical frequency times 2 pi r. So I plugged that into my calculator, and I got that the critical velocity is 0.44 meters per second. And when I plug that value in here, along with plugging in r equals 0.12 meters, and for r there, and 9.8 meters per second squared, and for g, I get that mu s is 0.16. And this works out great, right? Because here in this equation here, in the denominator, I have a 9.8 meters per second squared and a unit of meters there. So there's meters squared per second squared in the denominator. In the numerator, we have a velocity that's squared, so it's in meters per second and it's squared. So we have a meters per second squared in the numerator and a meters per second squared in the denominator. And so this quantity on the right-hand side here is unitless. And that's good because we know that the coefficient of friction is also a unitless quantity. So that's a nice check on this answer. And another thing, for the most part, mu static, mu kinetic are, for most materials, it's less than 1. So it's usually somewhere between 0 and 1. This looks like a very reasonable value. Okay, so let's go on and do one more problem. This one is a little bit tougher. This is from an old midterm exam. Okay, so some of you might have been on a carnival ride like this before. It shows a whole bunch of swings going around, right? The way that this amusement park ride works is that there is a swing ride. The structure consists of a horizontal rotating circular platform of diameter d, from which seats of mass n are suspended at the end of massless chains of length L. When the system rotates at constant speed with all seats empty, the chains swing outward, making an angle theta with the vertical. And you are asked then to find a whole bunch of different quantities. This is an exam question, so the first one explicitly just asks you draw a free body diagram. Eventually you're going to find properties like the tension and the speed and period and things like that. Okay, I have posted down below a PDF with all of these example problems. So hopefully you've already downloaded that for doing the previous two problems. But if you haven't, download that. Try this one out. This will be good practice for your exam. And then you can come back and see how I did it. Okay, so I'm going to assume that you've done that, and now I'm going to solve the problem. So there's two forces involved here. We have weight pulling down, mg, and a tension force up along the string, T. So that's a fairly easy free body diagram, not too difficult. Part B is you're supposed to determine the tension in the chain. Now this one is not that different than one of the example problems we did in the first video. I can set up a coordinate axes here. Let's say this is x and that is y. And I know that as these seats go around, they don't, their height does not change, right? They're only going in a uniform circular path, so that's great. That means that in the y component here, there is no acceleration, right? AY equals 0. Well, if AY equals 0, that then means that the sum of the forces in y is also going to be equal to 0. So let's get the sum of the forces in y. Well, there's mg, which is pointing in the negative y direction, right? So I have, right, this is equal to Fg plus the tension force, the y component of the tension force going up. So this is minus mg plus the tension force, the y component. And I'm given this angle theta. Oh, by the way, I don't know if I pointed this out before, but it says note, give answers for B, C, D, and E in terms of the given quantities D, M, L, and theta. So we're given this diameter, we're given theta, this angle here, we're given L, the length of this string, and we're asked to find these quantities in terms of those symbolic numbers. So Ty then is this component of the tension pointing up in this direction, Ty. Ty there, and there's Tx pointing in that x direction there. Ty, of course, is just T times cosine theta. So I have that this is minus mg plus T times cosine theta. And that means that tension times cosine theta is equal to mass times gravity. Or in other words, tension is equal to mass times gravity divided by cosine of theta. So I was asked to find the tension in terms of GL, theta, and D. So I am done. Got the tension. Now, this is very, very common in a lot of these free body diagram problems where you have to find kind of intermediate quantities before you can go right to the heart of what you want, which in the case of these circular motion type problems is to find periods and things like that. Okay, so part C, determine the centripetal acceleration of each seat. So previously in part B, I'd been interested in the y components. Now I'm going to be looking at the radial components. So I know that F centripetal is equal to mass times the radial acceleration. The radial acceleration at this time slice here would be in the the acceleration in the x direction. So this would be ax. So I can sum together then. I can sum together the forces in the x direction. So sum over all of the forces, right? All of the many, many forces in the x direction. Of course, in this case, there's only one, right? It's Tx, the tension, the x component of the tension, which is just T times sine theta. In this case, right, we already used, when you used Ty as T times cosine theta, then you kind of know that Tx is T sine theta, because there's only one trig left. Okay. Now, I also know, right, that this is going to be equal to mv squared over r. And v is the same. It's going around in a uniform manner, so I can use all of the equations of uniform circular motion. That's great. Okay, so I'm asked then to find the centripetal acceleration. The centripetal acceleration would just be a radial, right? It's equal to a radial. I could write a centripetal if I wanted to. It's equal to, right, just by this this equation here, divide both sides of this equation by m. Right? It's equal to T sine theta divided by m. Okay, I can plug in my T from part B there, and this would be equal to, then I have mg over cosine theta in for T. What is that, sine theta over m? Okay, well, you see that the m's cancel out, and I just have g sine over cosine is tangent. So g tangent theta. All right, that's my centripetal acceleration. Great. Now, let's go on to part D and E. Part D asks to determine the speed of each seat. So, previously, we had that the radial acceleration was g tangent theta. I can set g tangent theta equal to mv squared over r and solve for r. mv squared over r is equal to g times tangent theta. Well, I'm sorry, I don't need that m. So this was the radial acceleration here, and we know that the radial acceleration is v squared over r. And we're going to determine the speed of each seat. Now, there is something important to note in here, this r. So what is this r? Because remember, there's no r given to us. There was a d and an l and a theta, but there was no r given to us. Let's take a look back at the picture, and I will use green here, because we haven't used that one yet, and I'm even going to zoom in. All right, this distance here was d, and when we're looking for that distance r, this is the part that people who took this particular exam had the most trouble with. That r is always the distance between the object and its center of motion. So the axis of rotation is running right through here, right down the middle of this thing. So r is it's not L and it's not D, right? It's this distance that goes from here over across to here. Okay? That distance. So there's a part here going from the center of rotation out to the edge of where the string is tethered on to the machine, right? And that's just d over 2 is that length. And then there's this other part here, right? And this part here is, well, this length of the string is L, and the angle of theta is there. So L times sine is opposite over hypotenuse. So if I take sine theta, multiply the hypotenuse L, I would get this opposite angle here, or this opposite side length here. So L times sine theta would be that distance there. So R then is going to be equal to L sine theta plus d over 2. Okay. Now, I know this is kind of one of those things that it looks easy when I figure it out for you. It doesn't always look so easy. It doesn't look so easy on tests. So, all right, I'm going to, well, I'll just redraw it on the next page. So R was equal to L sine theta plus d over 2. Okay, now going back to our original thing, I can plug this in for R and solve for V. Of course, V is going to be, well, V squared will be G R tangent theta. Take the square root of both sides and get rid of that square up there. V is root GR tangent theta, and I can take R and bring it in, substitute it in there so that I'm answering in terms of known quantities. I have the G tangent theta times L sine theta plus d over 2. And that is my answer. The speed of each seat is root g tangent theta times quantity L sine theta plus d over 2. All right, now finally determine the period, which is the time for one full rotation going all the way around. All right, now remember, uniform circular motion, or UCM, implies that velocity is equal to 2 pi r over t. So we want the period t. In that case, t is 2 pi r over v. So I have v in terms of r here. I'll substitute that in first. This would be 2 pi times r over root g r tangent theta. Okay. I can cancel out, so we have a root r in the denominator and an r in the numerator. So I can cancel out this and make that a root r on the top. And so this would be 2 pi over root g tangent theta times the square root of r. So the square root of, now I'm going to plug this in there, L sine theta plus d over 2. Okay. That is the speed of each seat as this thing goes around. Now, I hope that was helpful for you. Just a quick few things to recap what's important here and what students often forget is that do not put centripetal forces on your free body diagram. Also, you sometimes have to solve for, use the components where you aren't necessarily interested in, where they might have those components that might not have anything to do with the with the rotational plane at all, but that you might know certain information about them if you think hard. So, like, for example, in this case, we knew that the acceleration in y was going to be 0, and that helped us find the tension in terms of given quantities, even though the rotation was entirely in the x-plane. Another thing to remember is that you don't put centripetal forces on your free body diagram, and instead, the centripetal force is a mathematical construct that's made up of these physical things that actually do make it onto your free body diagram. And then you can always, you always have to be careful with things like this radius r here, for example. It's always going to be the distance from the object to its center of motion. So that's, like I said, a lot of the students had a tough time with that part on this particular example problem, or this particular midterm problem. So I hope this was useful for you, and I hope that everybody does really well on these problems on their homework and on the exam.